Alessandro,
Oh, sorry, I was just saying thank you for coming.
Of course. Yeah, so what we thought we'd do is that we have, since I gave a talk already a little while ago, that we just had Jacob and Nick give sort of maybe a 10-minute sort of presentation each on their work. And then I also have, just because you guys, several of you guys were asking me in the past about sort of internships possible, is that I prepared sort of 2 websites, or I just want to quickly highlight 2 websites of sort of programs at LBL that exist. I just want to, I'll show them, and then I'll put the links, of course, in the chat as well. And then we can take your questions. So I don't know how you guys, Nick, Jacob, how you guys want to, which order you want to go.
I'm happy to go first unless Jacob has a strong preference.
No, absolutely not. Go ahead.
Okay.
Okay.
Let me see if I can share.
Just make you host.
Excellent. Thank you.
Okay. You should be able to share now.
Got it. Can you see my screen?
Yes.
Awesome. Let me make sure I can see the chat as well. Excellent. Yeah, so please feel free to interrupt and ask questions or put any questions in the chat as I'm going. So nice to meet you all. Thank you very much for having us today. It's a real pleasure to be able to talk about some of my research outside of Berkeley. And so what I'm going to be telling you about is at least how I approach the hunt for dark matter. So maybe you've heard about this. If not, I'll try and give you a bit of a review about why we're so convinced that there is this missing mass in the universe that we collectively refer to as dark matter. And I'll tell you about some of the ideas I'm really excited about as to what this might actually be. So to begin with, let me at least stress one part of what dark matter is, and it's a form of matter. So I'll give you some examples of matter. There's me on the left, cheesecake, and another example you might be familiar with is the sun. But of course, none of these are examples of dark matter. And the reason I know that has to be true is because we can see them. And so sort of the defining property of whatever this dark matter is, and I'll come to describe this in more detail in a moment or two, is that we can't see it. So none of these are examples of dark matter, but they are examples of matter. And one of the questions that I think maybe seems like a bit of a simple question, but I think is actually the answer to this is somewhat profound, is that if you find out that there's this huge amount or potentially of additional substance in the universe, or at least some new component to it, you might wonder, well, what fraction of the universe is actually made of this missing component? So, maybe you would imagine that the world is set up such that it's just going to be 50-50, that it's the stuff that makes up cheesecake and the stuff that makes up dark matter. But given that we can't see this stuff, maybe you would think only some tiny fraction of it is, so maybe 1%, or maybe you think it's going to be the absolute dominant component. So, I mean, maybe some of you know the answer, but if you don't, I mean, even if you do, or you're just interested, please throw a suggestion out in the chat, or feel free to interrupt me if you have any thoughts on what this is. E and D. This is sort of an ask the audience type thing. Oh my goodness. Okay, so we've got a very well-informed audience here, which is awesome, because the actual answer is pretty much D, as many of you have correctly said, or E wasn't too far off. But so, I mean, there's 2 things to note about the fact that we can see that it's actually close to 84%. The fact that I can say it so precisely tells us that we actually know a lot about this. Even though we can't see it, I can tell you that roughly 84% of the matter in the universe is made of this substance. But I actually think it's quite interesting that this value is close to 50-50. I mean, if the dark matter and regular matter had nothing to do with each other, you might have imagined that it was either going to be some tiny fraction of the universe or totally dominate. The fact that it turns out that it's almost 50-50 of the matter in the universe, at least is a hint, I think, that whatever this dark matter is, and while we're still unsure, it might have something to do with the other type of matter. And that's collectively referred to as the standard model, which is what I'm showing in orange here.
Hey, Nick, great question. There's some question in the chat. Shall I read them out to you? You want to read them yourself?
Oh, good.
Or answer them at the end, however you want to do it.
That's fine. No, I'm happy So what exactly dark matter is, maybe I'll come to this in a moment. This is a very good question about where exactly it is, but maybe after I've gone into that in a bit more detail, that might already answer your question, but if it doesn't, please re-ask it. I'd be happy to discuss. But I think maybe I'd be going through too many of the details I'll describe in a moment, try to answer that now. So let me put it off for a second. So let me address the question, sort of, how can I be so confident and make precise statements about something that I can't even see? And really, it comes back to, sort of the fundamental physics is sort of encapsulated in this very simplistic animation here, which is a not quite to scale animation of the Earth orbiting around the sun. So, of course, famously, we understand what is the physical principle that dictates the dynamics of this problem is the gravitational interaction between the Earth and the sun. And in fact, we can understand a lot about what's happening here. For example, the mass of the sun is responsible for determining how fast the Earth orbits around, moves around in its orbit here. And in fact, our understanding of gravity is such that I posit that even if we couldn't see the sun, putting aside any associated biological catastrophe, we would still be able to infer that something was there, because we know just like things don't just move without some sort of, won't move in a circular orbit without something pulling on them. And so we could infer that there actually had to be something at the center of the solar system, even if we couldn't see it. And we would go further, just from the motion of the planets, we could actually infer the mass of whatever was missing here in the center. And so actually, this is exactly how we infer the existence of dark matter. And I'll show you in more detail how we do that in a moment. But basically, we have such faith in our theory of gravity that when we seem to see something that looks paradoxical, like a planet orbiting around nothing, we can infer that actually there has to be something in that nothing. And this missing substance is dark matter. So this is, of course, a real cartoon representation of what's going on. And I'll come to the more realistic thing in a second, but I also see there's another question in the chat. Oh, good. Yes, I'm not actually sure. Oh, how did I do this? Sorry, up a window. I'm not actually sure in this context what the rotation of the sun is meant to do other than look aesthetically pleasing. That's got nothing to do with the physics here at all, actually. That's a bit misleading, but thanks for pointing that out. That's a good question to ask. Yeah, that's it. The question about there's another question about whether gravity is flawed. That's a really good question as well. Actually, it seems like there's a ton of questions. Maybe I'll just put some of these on pause at the moment rather than break the flow up and come to these at the end. But these are some really good questions that I just can't answer in 10 seconds or so. So let me just move on a little bit. And I'll come back to them later. So now let me turn to a more realistic situation. Obviously, that was a cartoon animation, and already, as the questions have pointed out, there were some aspects to it that are a bit misleading. So let me turn to now the more realistic situation. And actually, what happened here was back in the, well, not me particularly, but back in the 1960s, there were some pioneering astronomers in the form of Vera Rubin and Kent Ford, who were studying our nearest neighbor in the universe, the Andromeda Galaxy, which is the galaxy I'm showing you in this slide here. And what they asked was sort of an upgraded version of this question of what is the orbit of the planets in the solar system. They asked, what is the orbit of the stars around the center of the galaxy in the Andromeda Galaxy? So you can think that a lot of the physics of gravity are really going to be at play here in this object as well. And of course, if you're not aware of her at all, it's definitely worth pointing out Vera Rubin, who is really, I think, as I'll describe in a moment, this work that she did in this paper and also some subsequent work really was underpinned our modern understanding of dark matter. I mean, there'd been hints dating back to the 30s that maybe dark matter existed, but the community, I mean, the evidence wasn't so robust. It was really her work with Ken Ford that convinced the community that this dark matter problem existed. And I just want to roughly point out to you how she did this very quickly here. So we can actually make a prediction for how fast we think the stars should be orbiting around the Andromeda Galaxy. Essentially, it's going to be related to how much mass is in this galaxy. And while we may not know exactly where all the matter is and how it's distributed, we do know that as we move further and further out, especially beyond where we can see matter in this image, the speed should begin to drop. And this is sort of what's encapsulated here. I'm showing you the rotational velocity. And of course, there's like this flip in the middle because it's rotating as a disk around the center. So this is what we expected before Vera Rubin went and did her precise measurements. This is what was actually seen. You can see that the speeds are much faster than what was predicted. And also what is quite shocking is that the values aren't going to zero outside where you can see mass. So it seems that this object, I mean, if we're going to say that we trust our theory of gravity, the only way to reconcile what we're seeing in the data here is that there must be a huge amount of additional mass in this galaxy beyond what we can already see, and also extending out well beyond where we can actually see this galaxy here. And so this was the first really robust hint that galaxy-sized objects contain a huge amount of missing mass, and this is collectively what is referred to as dark matter. And in the half century since Vera Rubin's pioneering work, as we've looked again and again throughout the universe at all different sized objects, we again see there's missing mass, and we need this dark matter to be there. And because we can make such precise predictions, we can now determine that this is how we have this 84% number I showed you earlier. And in fact, there's observations all the way back to some of the earliest times of the universe, which is the form of the cosmic microwave background. And even there, we need dark matter to exist. So this is how we have this growing picture that there is this missing mass, and we know how much there is quite precisely. So in my research, I asked the question of what is this dark matter made of? And I'm quite convinced that our theory of gravity is roughly correct. And actually what's going on is that there's just some new particle that we haven't discovered yet that just doesn't interact very strongly with light. And this is this so-called particle dark matter hypothesis. So in some senses, this picture is very simplistic. We have all the particles we know about in the universe. We just need to add one more, and then that is what dark matter is going to be. But then, of course, the question that we still don't understand is, what is this one new particle? And here is where we have to admit that we're extremely ignorant. Because if you ask sort of a fundamental question about a particle, like one thing you might use to describe it is, what is its mass? Like we know the mass of the electron, we know the mass of the proton, for instance. What would the mass of this dark matter particle be? And the truth is we have almost no idea. It could exist over an enormous number of orders of magnitude and still be consistent with all the observations I showed you previously. So here I'm actually showing you sort of a ruler of particle mass where lighter masses are to the left and heavier masses are to the right. And roughly in the middle is what is particle physicists call a GeV. We're measuring mass in units of energy thanks to Einstein. And as you can see, at the bottom, a GeV is a very small amount of mass in everyday quantities, but it's a reasonably in the middle particle. It's about the mass of a proton. And on the axis I'm showing you here, the units are logarithmic. So an EV is 1/billionth of a GeV. For example, and an EeV is a billion GeV. So you can see that the numbers here are enormous, and even things go well beyond that. And the dark matter mass could live anywhere along here. And so this is a challenge, but I think it's a very interesting challenge because where you look on the particle ruler, the actual behavior of dark matter can change dramatically. For example, if dark matter is super light, then there'll be so many of these particles around that it actually takes on a collective behavior and actually begins to act like a wave. And so actually here at the location of the Earth, we would think there's some dark matter wave that's undulating through us. And if we can pick up a design a sensitive enough detector, we could measure that wave. And in my research, I think about ways of determining whether that's a wave. But on the other end of the spectrum, you could have that dark matter is the heaviest particle in the universe. And in fact, in principle, it can be all the way up to this MP, which is the so-called Planck mass. And the reason why if it was a particle, it couldn't be any heavier than that is because it would actually fall into its own event horizon and just become a black hole. And dark matter actually could be black holes, but that's beyond what I usually think about in my day job. So I'll just draw a boundary there. So the idea is if this dark matter was a particle that was all the way at the Planck scale, it would have so much energy that if it occasionally decayed, you would actually get a macroscopic amount of energy coming out. You can compute through E equals mc squared that if you have this particle that is 10 to the 19 times the mass of a proton, it would release about the same amount of energy as 500 kilograms of TNT exploding. So there'd be little explosions happening throughout the universe. They would produce enormously energetic particles. So I've actually depicted these as cricket balls here because you would actually have particles flying throughout the universe with the kinetic energy of macroscopic objects like a baseball pitch or something I'm more familiar with would be a cricket ball. And the idea then is we would go and try and look for these extremely energetic particles. And if we see some of them, this might actually give us a hint that we're finally determining what dark matter is made of. So that's another way that I'm trying to figure out what dark matter could be. But that's just two tastes of how we might actually determine what dark matter is. I mean, really, it is very much an open question that while I'm quite convinced whatever dark matter is, it has to be some new particle. What exactly that particle is, I think is very much an open question. Good, so I see that there's been a ton of questions in the chat here. I'm very happy to take them now, but also I know there's a discussion afterwards and I maybe don't want to dominate too much of the time. So potentially I could take one or two now, or we could have Jacob speak and we could pick up the discussion afterwards.
I mean, what do you guys think? What do you guys think is better?
Okay, well, we will have a section where we will talk about dark matter. So if you want, we could do it then. But if you think your thoughts will get confused, then we could do it now.
Maybe I can try and give the very short answer to some of the questions that have been put here. And I mean, there's some really good questions. And if any of the answers people find are particularly unsatisfying, we can come back to them in the discussion session. So firstly, there was a question from Tyler about, is it the void in between galaxies? Actually, no, largely dark matter is still even where the galaxies are. This was sort of, I mean, this was before I presented that. So we think we roughly know where dark matter is, and it's mostly not in the void between galaxies, although there is some dark matter, and in fact, regular matter there. Good, and then there was this good observation that the motion of the sun was slightly misleading. Thank you for pointing that out. It is possible that our theory of gravity is flawed. There was a question from Jacob, but there is ways of testing that. And again, it does appear that our theory of gravity is correct. All the suggestions people have made for how gravity could be modified produce predictions that just don't seem to agree with what we see in the real world. And there's a lot more that can be said about this. But while that's a very fair idea ahead of time, it doesn't appear to be supported by data. Good. There's a question from Paxton about this is a similar way to how we discover some black holes. I guess I'm not exactly sure what slide that was on. Paxton, if you're there, feel free to clarify either in the chat or unmute yourself.
I think it came up when, oh, sorry, Tyler, you should obviously say it.
I think it was in the slide where you were talking about how even if we couldn't see the sun and we saw the Earth moving, we could, you know, predict that there was something there. Yeah, you're exactly right. Like most of the black holes we know about, and also the supermassive black hole at the center of our Milky Way, we see through how it impacts nearby objects, for instance. So often they're in binaries, and we see one thing orbiting around something else, so it's exactly like you described. So that's exactly right. Yeah. Oh God, there's a lot of good questions here. Is it unreasonable to infer that there could be a force pushing on the outside? Do you mean like, I guess that I'm not quite sure what the question here means, but potentially like outside the entire universe or something like this, or what is, maybe I'm misinterpreting that question here from Felipe.
Yeah, so when you were talking about the cartoon of the Earth was going around the sun, and then you remove the sun from that cartoon, could there be any way that like there's not something in the middle, but something on the outside that's causing that rotation of the Earth?
Yeah, so what, good. Yeah, no, that's an interesting suggestion. So what you know is that there's a force pushing it inwards. That's how it maintains a circular orbit. So in principle, something on the outside could cook that up. And if we were just looking at one system in isolation, maybe you could think about whether there's some force acting on these things from the outside that we can't see. But I think when you then start to see that this is happening, where most of this motion is happening is towards the center of galaxies, I think you could test that and eventually rule that out. Well, that's an interesting suggestion that, yeah, I need to think more about. I mean, in principle, a priori, something like that might be possible, but I think that where we are at the moment, all the observations seem to be much more consistent. There's actually something at the center pulling largely. But dark matter isn't just at the center of galaxies, it's all spread out. And there's more I could say about that, but let me leave that for later on. It's an interesting suggestion. I remember, goodness. Okay, I'm also conscious that I was trying to give short answers, but the questions are coming as fast as I'm answering them. Maybe I'll just cut it short there. I'm happy to come to any of these questions in the question time, but I'm just conscious of taking up too much of the time. Maybe I'll pass it over to Jacob for the moment.
Yeah, we will have more time to
I'll keep track of the questions also.
Thanks, Christian. Yeah.
We can answer the rest of the questions later when it comes to the question asking section.
I'll be very happy to. Thanks everyone for the fantastic questions. That was really engaging.
Nicholas, if you want Jacob to share, you need to make him the host.
Right. Yes, or just
Okay,
activate sharing. Yes.
Nick, I think you're the host now, so you probably have to make, oh, you did, okay.
There we go, excellent, okay. Right. Can everyone see my slides here?
Yes.
Yes. Okay, great, excellent. All right, yes, so thank you everyone for the opportunity to come and talk to you all. This has already been a lot of fun, just watching Nick deal with all the very interesting questions that you've all cooked up. So I'm excited to see what else you'll have in the question and answer section. So I'm going to talk about a very different topic, which will be kind of an overall survey of some very small parts of string theory and then how it relates to some of the work that I've done and then I'm working on right now. All right, okay, hold on one second. There we go. Okay, good. So first, we'll start with the kind of obvious question, what is string theory? And I think one of the more interesting aspects of this is that the answer you'll get depends very much on who you ask. And I don't mean that, you find some random person on the street and you ask, what is string theory? And then you ask like a physicist. If you ask different physicists who work on string theory, you'll get different answers because it's a very multifaceted aspect of physics, and people work on very specific subdivisions of it. So one answer you might get is that string theory is the theory of everything. So what this means is that we have like the particle zoo that Nick just showed, is that you have all of the particles that we know about, electrons, protons, all these sort of things. And string theory can encapsulate all of those and more. So it encapsulates all the bosons that we know about, the matter that we see, and then even gravitons, and it unifies them in a very cohesive sort of picture. So this means that it's a theory of everything. You might also get the answer that it's a model of quantum gravity. So this is kind of related to the theory of everything because gravity is included in the everything, but this is a little bit distinct because as far as we know, string theory is really the only viable model of quantum gravity that we have. So it's a very special aspect of string theory. And in fact, string theory has revealed a lot of interesting features about quantum gravity that I'll get to later on in the talk. So I think that it's fair to say that this is a very different subject. And in fact, there are some people who work just on this part of string theory. They don't care about the fact that it's a theory of everything so much. Another thing, which might be a little bit less familiar to all of you, is that some people would describe string theory as a mathematical construct that has a web of dualities. So what I mean by this is that you have a whole bunch of different models and theories that are connected to one another within the framework that is string theory. So you can kind of think of string theory as not necessarily one model, but kind of a way to connect various different types of models. And again, I'll get to this a little bit more towards the end. And then finally, some people would say that string theory is really a wealth of mathematics, that if you're really interested more on math than in the application of string theory to physics, you have a lot of interesting features to discover about geometry, topology, all sorts of neat stuff. So some people are just really interested in the math. And this is not just abstract art I have down here on the bottom. It actually is supposed to mean something significant, but it just looks really cool as well. Okay. So continuing on to try and get a handle on some of this overview that I just gave, is that here we've got the standard model depicted in this really neat way. So we've got the Higgs particle, the gauge bosons, and then all of the fermions. And so what string theory would say is that these are not just point particles, that they are different types of oscillations of strings. And one thing I should note is that there are questions. I think I'll do what Nick did, and come to them at the very end. So just remember where you asked the question so that I can ask you later. All right, so yeah, so in string theory, all the particles that we see would correspond to different types of oscillations of string. So here you have different kind of oscillations of a closed string loop. And so each one of these different kind of modes would correspond to different particles. Now, what that means then is that when you have interactions between particles, that also looks a little bit different. So for instance, here on the left-hand side, I have, let's say, an electron and its antiparticle, a positron. They are interacting by exchanging a photon. That's what this diagram here on the left means. In string theory, what that looks like is that it looks like a bunch of tubes that are connected. And so this is how interactions look. So we're kind of, if you will, smearing out the picture of particles that we have from everyday life. And in particular, I'll mention that one type of vibration corresponds to a graviton. So a graviton is supposed to be the particle of gravity, if you will, which in a kind of heuristic manner of saying that. And so what that means is that string theory automatically is a quantum theory of gravity, because it is a quantum theory and it has gravity in it, and therefore it is a quantum theory of gravity, and it also happens to be a consistent quantum theory of gravity. Okay, so that's the rough overview. Now, of course, you can imagine that this is a little bit simplistic of a picture. So this, from what I've described on this slide, you might say, oh, everything's okay. We have a perfect description of the standard model of particle physics and all this stuff. So, we've done everything. It's not even close to that. So the first struggle that I should really discuss is the fact that there isn't just a string theory. There are at least most people say there are 5 different consistent string theories. So those are type 1, type 2A, type 2B, and then the SO32 heterotic and the E8 cross E8 heterotic string. So they all have very specific features, but it's going to be too much to talk about them in detail at this point. But again, you can always ask questions later. But the point is that there are 5 of these. And the kind of surprising feature that was found is that they live in 10 dimensions. And of course, we live in 4, well, yeah, so 3 plus 1, so 4 dimensions, 3 space, 1 time. And so, you know, right at the beginning here, we would see that there's some kind of problem, that clearly what we've developed here in these 5 10-dimensional string theories doesn't correlate to what we see in the real world. But you shouldn't lose hope, because there's a way to get around this. What you need to do is compactify some of these dimensions. So what that means is that rather than have an infinitely large direction in space, you make it a small, compact surface. So for example, you can imagine kind of thinking of a sheet of paper that you then roll up into a cylinder, and then you match the ends of the cylinder together and you get a donut or a torus. So this is a very simple way to do that. So one example is that you can take 6 of the dimensions and make 3 donuts, and then you have 4 dimensions of space-time, and then you have your 3 donuts to go along with it. Unfortunately, while this is very simple, it turns out that the theory you get doesn't look like anything that we would expect from particle physics, and so this is kind of a little bit too simple. But what you can do is you can cook up much more complex stuff. And so you, if you've been around Wikipedia or other popular science stuff about string theory, you've probably seen an image that kind of looks like what I have here. So this is what's a depiction of Calabi-Yau surface. So what that's supposed to mean is that it's just some kind of 6-dimensional surface. So you, rather than making a bunch of donuts, you've somehow warped everything together into something much more complex. So you say, okay, we have all of these different surfaces, but why is that important? Well, it turns out that the geometry and the topology of these 6-dimensional surfaces determines the 4D physics. So what that means is that it tells you what types of particles you get, what numbers of particles, the masses and the interactions and all these sorts of things. So really the 4-dimensional physics that we see is dependent on what the shape of those 6 compactified dimensions are. But there are some general features. There are, a lot of work has been dedicated to figure out what kind of general features you could expect. And I'll just list some of them here. So for example, you're going to have gravity in your spectrum always. So then you will always have a quantum theory of gravity. So that's nice. Typically what people say is that you need supersymmetry in order for things to make sense. So I can explain more about that in the question and answer section, but typically you need some amount of supersymmetry. And when you have supersymmetry and gravity, that turns into supergravity, which is its own unique, interesting thing. And generically, you also have grand unified theory. So this is, of course, in the spirit of the fact that you can combine the electromagnetic force and the weak force into the electroweak force, and then hopefully you can combine that with the strong force at some higher energy scale. So in string theories, you typically get this right away, that you've got some theory for interactions, and then these eventually break down in the way that we understand that the electroweak force breaks into electromagnetism and the weak force. Okay, so this is my last slide on this topic, I think. Let me just double check. Oh, wait. Oh, sorry. That was a spoiler. So sorry about that. So what I'll just mention right here is that this is what most of my work that I've done with my advisor has been on in string theory, has been understanding string theory as a theory of everything and how it relates to particle physics. And it's a very difficult subject because we really don't have a good understanding on how exactly to get realistic, good particle physics out of these compactifications. We can get approximations to it, and that's what I've worked on, but get something that's actually completely viable is still very much an open question, I would say. So for the spoiler, what I'll mention is that I was asked for equations in my PowerPoint, and so I've decided to give you this. So this is a horrific mess, and it's really just to show you that these things can be quite complicated. So what this is supposed to be is it corresponds to one of the 5 types of string theory that I showed you. It corresponds to the particle theory limit of that string theory. And what you can think of this mess as is the difference in kinetic and potential energy for the various particles that exist in that theory. So you're not expected to understand this. I just wanted to let you know about how much of a mess this can sometimes be, but I have more useful equations later on. Okay, so that concludes pretty much the discussion that I wanted to do about string theory as a theory of everything, which has been most of my work on the topic of string theory in the past. But then I was also asked to talk about holography, and so that'll be the rest of this talk, and it does relate to some of the stuff that I'm currently working on. So by studying certain compactifications, a rather interesting phenomenon was found within string theory, and that's what people describe as holography. So I think the best way to first get into this idea of holography is to look at a concrete example. So what I have here depicted in this kind of soup can thing is the standard example of a holographic setup. So inside the soup can, so this three-dimensional space, we've got a vertical, an angular direction, so we can go around in circles, and then a radial component because we can go in and out like this. So this is inside the soup can is 3 dimensions. In there, we've got a 3-dimensional quantum theory of gravity. And so here it's labeled by anti-de Sitter space, which is a particular type of gravity that I won't go too much into. But the point is, inside the soup can, we have gravity, in particular quantum gravity. On the boundary, though, of the soup can, that is 2-dimensional because we've got the vertical direction, which again is the time actually here. And then we've got a part where you can go around the soup can. So that's the kind of angular movement. That is a quantum theory without gravity. And the point here is that you can do calculations in the 3D gravity and in the 2D quantum theory, and you'll get agreement once you know the correct way to match things. So what's happening is that the theory on the boundary knows about the stuff that the theory on the interior can actually do, and vice versa. So you have what's called a holographic duality here. And that's exactly what I have here. And so in the very first, second slide of my talk, I described string theory as a network of dualities, and one type of duality is this holographic duality. So it's holographic here because we're relating a 3-dimensional theory to a 2-dimensional one. So you kind of have the idea of a hologram encoding of the 2D theory as a hologram encoding the information of the 3D one. And so you can generalize this idea to a holographic principle, which says that in quantum gravity, the information of a region of space-time is encoded in its boundary. So what I'll mention here is that this is a very much kind of still speculative idea. So what I've given you here is a very specific example that we know pretty well works. The holographic principle, as I've stated it here, is a much more general notion that has some support, but it's not as established. So I wouldn't say that it's necessarily a principle. It's more of a guess that we haven't found a concrete counterexample to yet. And it seems to be working, but there's still a lot of work in this direction. So to make things a little bit more grounded here, you can also consider evidence for this holographic principle from black hole entropy. So this is, of course, famously established by Bekenstein and Hawking, which says that the entropy of a black hole is proportional to its area. So the area of the event horizon, I should say. So that's A right here. And then you've got other fundamental constants, the speed of light, Planck's constant, and G, Newton's constant. And I was also asked to describe a little bit what entropy is supposed to mean. So what does entropy mean? If you look up, the definition of entropy, you'll read it as the measure of disorder. But we can kind of look at this in a simple example. So this is one way to assign entropy to a system is that you have the entropy is equal to a constant here, K, which we won't worry about, and then the log of what's called the microstates. So let's try and figure out what this equation is supposed to mean. So let's consider a scenario where I have 2 boxes and then I'll have 2 particles. And I'll say 2 particles are in the left-hand box. So what that means is I have both particles here in the left-hand box. And the number of microstates is the number of configurations for which this can happen. Of course, since I only have 2 boxes and I have 2 particles, there's only 1 microstate. So there's only one way to have both particles in the left-hand box. So W here is equal to 1, and the logarithm of 1 is just 0. So that means that the entropy here is just 0. Now we can ask the same question for both particles on the right-hand side. And again, there's only one way to do this because we have only 2 boxes and 2 particles. So we put them on the right-hand side. And again, the entropy is 0 for this configuration. Then you can ask, well, what if I have only 1 particle on the left-hand side? In which case there are 2 ways to do it, because we can have 1 particle, the blue one here on the left-hand side, or the red one. And so W is equal to 2, and then the entropy is no longer 0. It's this constant that I have here, K, and then log of 2. So this is the idea of entropy as a measure of disorder, is that the more microstates you have, the more entropy you are. And the more microstates, the less ordered you can think of it as. Because if you have 2 particles in one box or 2 particles in the other box, you can consider that more ordered. So this is not doing the concept of entropy justice at all, but this is kind of a rough idea that I was asked to do. So again, we can talk about it more. This leads to a natural question, though, which is, if a black hole has entropy, what are its microstates? And maybe that was asked in the chat. I'm not checking it right now, but this is the natural question to ask. And the answer is that in string theory, for certain scenarios, you can actually count these, but it's only for some black holes in certain setups. So this is still very much a question that people consider, since you can only, there are limited results along this direction so far. All right, and so the very last thing that I'll talk about is that in this holographic setup, you can also define entropy. And what you'll find is that on the boundary theory, so the label of the soup can, you can find that the entropy of a region of that boundary is actually given by a formula very similar to the one for the black hole, but rather than the area of event horizon, you have an area of a surface that extends into the soup can. So the way that this looks is you've got this, the label of the soup can, you've got like a net that exists that goes into the soup can, and the area of that net will give you the entropy of that surface, the area on the surface. So that area on the surface being big A right here. And then partial A, or the this funny symbol A here, that's just the boundary. So that's not too important for what we're considering. So this is really a lightning review of just some concepts in holography. Again, there's so much more to talk about, but I don't really have the time for it. The last comment that I'll make here is that that holography and the holographic principle, or holographic duality, however you'd like to say it, appears to be a remarkably robust sort of phenomenon. And so you can even use holographic principles for very weird theories of gravity in 2 and 3 space-time dimensions, where you actually don't have gravity in the conventional sense. And so this is something that I'm also working on right now. All right, and so with that, I'm going to get to the conclusion. So some of the kind of interesting questions that I've kind of worked on in the past, and I'm continuing to work on, and not just me, but lots of people that work on this. Some of the interesting questions that people pursue are, can you actually get a viable version of the standard model plus dark matter and maybe extra stuff that we don't know about yet from string compactifications? Again, there's been a lot of work on this, but we still don't have a clear picture or a good understanding of how to do this in the most general sense to get to the actual standard model. And then another one that I didn't talk about too much, but it's also very interesting, is can you actually get cosmology to work in string compactification? So that means things like dark energy and primordial inflation and other aspects of the universe. And then for on the holographic front, you can ask questions like, how far does the holographic principle extend? So as I mentioned, it seems to be very, very robust, and you can get all sorts of weird stuff out of it, but are there some limits? Is there some scenarios where it actually doesn't work? And so then another very natural question is about whether we should consider the holographic principle to be a fundamental idea, or if it's the consequence of some other feature of quantum gravity that we just don't understand. And of course, this is just a small snippet into an absolutely enormous subject. And so, yeah, that's all I have for today.
Wow.
Yes, it's up to stare. There we go. Okay.
Did you want to answer a couple of the questions in the chat, or would you like to go directly into the Q&A?
So of course, it all depends on you guys. I'm happy to address some of them. Maybe I can address a few for a few moments, and then if Nick wants to circle back to some of the ones he didn't do, we can switch off for a couple minutes until we actually get through the debt of questions that we've accrued here. Does that sound good to you, Nick?
If you prefer, we can also just go through the categories as well.
So it's completely up to you. Yeah, I have no strong preferences.
Maybe you should do what Nick did, no, and just go quickly through,
Sure.
Since people put the effort to put the questions in.
Yeah, I think that sounds good. Okay, so let me try and find where the cutoff is.
Started about 3:56, which is you have the time on it. That's what I seem to see.
All right, so Felipe, how do you create a theory like string theory that doesn't even exist in a dimension that we understand, the 10 dimensions? All right, so yeah, I'm a little bit, I'm not sure I completely understand the question, but I think from what I'm gathering is how do you formulate a string theory in 4 dimensions, for example? Felipe, if you want to clarify, if I get the right idea.
I'm not sure if I misunderstood, but on the slide that you were explaining the 5 types of string theories, you said that they exist in all 10 dimensions.
Right.
Like, how do we even know in what dimensions that they exist if we don't even like comprehend those dimensions?
Right. No, yeah. Okay. So that's actually a much more profound question than what I thought. So yeah, no, that is an excellent question. And so it actually, there's a very technical answer to that, which is has to do with the mathematical way that we formulate string theory. But the kind of intuitive answer is that when you formulate string theory, so you say, okay, there's some kind of object that's like a two-dimensional object that we call a string, and then you try to do the math, you try and formulate that question mathematically, and then you make it consistent with quantum mechanics. What you'll find is that there are certain a consistency criterion that you have to impose, and it turns out that when you impose those consistency criterion, you find out that it has to exist in 10 dimensions. At least this was, again, the first way that people formulated at the very beginning. Then after that, you learn, okay, what I can do is I can figure out clever ways to make some of the dimensions small, and I can still have a consistent theory. So it was actually completely by accident that you find that it's 10 dimensional. But really, you write down a very simple idea, and you try and make it consistent with quantum mechanics, and you find that it has to exist in 10 dimensions, at least in the simple way that they did it initially. So that's not super descriptive, but the only other words that I could put to it are very technical. So I think that's the best I can do as a short answer.
Yeah, that makes sense.
Yeah, great question. All right, so that's not a question. Okay. Yeah, okay, so there's another great question from Lev. If strings have an infinite number of vibrational frequencies, are there then an infinite number of different particles? Yeah, so that is an absolutely excellent question. And yes, so there are a whole tower of particles. This is how people describe it. So each one of the ways that a string can oscillate, then there are a whole bunch of particles that correspond to it. So then the question is, how do you make sense of such a thing? So the point is that when you're trying to develop a particle theory from some string compactification, is that you look only at the oscillations of the strings that have zero mass. So the reason for that is that the oscillations that have non-zero mass have masses that are far too energetic for us to care about. So the idea being that the kind of working paradigm of people who work in particle physics and string theory is that you look at the particles that have zero mass, and then you have some mechanism to give them mass. So of course, this in the standard model, this is like the Higgs mechanism. So you have some way to give the zero mass particles mass after you look at only the massless states. But technically, those massive states that you're talking about do exist, and there's been a lot of interesting ideas recently about how they might be important to quantum gravity as a whole, even if you don't see them in the low energy particles that we look at. Would the holography not work if the anti-de Sitter was not in 3D? Yeah, so no, it definitely works in higher dimensions. I only talked about 3D because that was what it looked like in the diagram there. But technically, you could even look at that kind of picture and assume that it's higher than 3 dimensions in the interior of the soup can. But I just did it because it's an easy way to visualize, and anything beyond 3D gets very difficult. Why does the diagram of antisystems have about tessellations at the end? Yeah, so that has to do with the geometry of the space. I mean, really, it's more of an artistic thing than anything else that people like to talk about it. But there is a relationship between these tessellations and the geometry of the anti-de Sitter space. But there is no physical reason about the tessellations. Like they don't necessarily. There isn't a real tessellation in the space. It's just an artistic thing that people like to put in the diagrams. Is there a mathematical set of microstates which is so I have trouble with Ryan's question about the set of microstates in which a hot object gets hotter rather than colder. So so reading that question, what I'm interpreting is if there's a way to understand how microstates correspond to temperature, or Ryan, if you would like to clarify that question.
Sure.
Yeah.
So you said that microstate, so the entropy, the spontaneity goes with probability, right? So that getting colder is more likely, right?
Sorry, no, I did not talk about spontaneity or even changes in temperature, though there is a temperature for black holes. Yeah, that's true.
So my question would be, if I don't know how to, I'll think about it. You can come back. We can go back to it.
Sure. Yeah. Whenever you formulate, then we can talk then. Do black holes decrease entropy since it brings matter together in one megastate? That being the singularity. So that's a great question by Tyler. So so a black hole is in a sense an object of maximal entropy, actually. But what a black hole will do is that it will eventually radiate away. But of course, astrophysical black holes will be much more interesting features with potentially absorbing objects. But in that case, I believe the correct statement is that you're always going to be increasing your entropy when you're absorbing things into a black hole. So this is just black hole thermodynamics, and it's really saying the statement that entropy always has to increase. And so as far as we know, black holes definitely still obey that feature of thermodynamics. Is there observational evidence that gravity is quantum? So I would, so that's a tricky question. So I would say that no one has observed a graviton. So that's true. But I would say that, so it depends on at what level you mean gravity is quantum, because there are effective ways to talk about gravity in a quantum theory. And there have been some tests of that. So there's one, I forget the name of the experiment, but it had to do with bouncing neutrons, I think it is, that was looking at the effect of gravitational potential on the interaction of gravitational potential with quantum mechanics. But I would say that that probably isn't what your definition of quantum gravity is in terms of looking at a graviton. So in that case, I would say no, but it's a very difficult question, I think, and it depends on what you mean by the interaction of gravity and quantum. So I think the rest of this, okay, so I think I have two more questions and then I'll pass it back to Ryan. I'm sorry, not Ryan, to Nick. I was reading Ryan here in the chat. So
before you do that, Jacob, can I just add one point to that last? I mean, there's this famous paper that is pretty accessible if people are interested by Freeman Dyson called "Is a Graviton Detectable?" I don't know if you're familiar with it, Jacob.
Oh, no, not in detail, no.
He walks through some thought experiments to see what would it even take to build an experiment that could see a single graviton the way we might see a single photon. And he concludes that you would need to build an instrument that would collapse into a black hole. You'd need so much mass in such a small area. So in principle, just the naive way you'd think about detecting a graviton appears to be impossible. And there's this really beautiful paper by Freeman Dyson that runs this through. So if you're interested in that point, have a look.
Oh, nice. Sorry.
Would we be able to understand that paper based with our level of physics?
But maybe not all of the technical details, but it's written like in a very just discussionary way. So there's, I mean, certainly the introductory parts of that, like maybe not all of the math, but it was like it's an area I don't work on and I understood it, but I mean, certainly some of it is accessible. So I can't promise all of it, but yeah.
Okay, cool.
All right, so I'm going to answer at least these two last questions and then pass it back to Nick or open up to the Q&A, whichever one the organizers would like. So I'll answer Alexander's question. So are the small dimensions continuous somehow across the universe, or are they in discrete places? So the idea would be that they exist everywhere in our four-dimensional space. They're just really tiny and we can't observe them through conventional means in the sense of being able to, move objects through it or something like this. So they would exist everywhere in what we think of as space-time. And then from Sarah, have scientists found a way to test for the existence of strings other than the mathematics of it? So I think that this is an absolutely excellent question. It really gets to this idea of, is string theory really science, or is it just some kind of, gobbledygook that people work on? So I would say that it's a complicated situation, because I would argue that at least when it comes to trying to build particle models out of string theory, is that we don't or cosmological models even, we don't understand enough of it to figure out a good way to answer the question of testing it. So you might ask the question of, okay, if I predict this spectrum of particles, I should be able to look for it. And you would say, okay, that's great and all, but we don't have necessarily good ways to understand what the masses of these particles are going to be, or even the way to generate these masses in a lot of scenarios, or even figure out how to make good cosmological models out of string theory. So I would say that in that front, there is no way to test for it, but it's not really the fault of string theory per se as not being testable. It's more of the fact that we don't understand it enough to be able to formulate concrete ways to test it. Now, so that's one aspect of it. The other aspect is that there are some ways where you could kind of turn this question around, and this is what some people have been working on recently, which is to say, can we figure out ways to, can we figure out criteria from string theory for the consistency of the particle physics that we see at lower energy, so stuff that we know about. And in which case you might be able to figure out a way to say, we can test string theory if there is a way to definitively prove that only string theory can give a consistent theory of quantum gravity or of the particle content that we see at low energies. So yeah, I would say that, and again, that also isn't developed enough to have a concrete answer. So that is very much under development. And the last thing that I'll just say here, and then I'll shut up and let Nick have it, is that I would argue that there are some aspects of string theory that aren't tested in the conventional sense of setting up an experiment, but rather in the sense of consistency of ideas in mathematics. So there's a lot of interesting mathematical concepts and ideas that have emerged from string theory, which give us the idea that even if it isn't the fundamental theory of quantum gravity or the theory of everything, it's not something that's completely worthless. So there are ways to test its ideas in a mathematical setting and see that there, is some value to it. Beyond just as a theory of everything, because after all, maybe it isn't the theory of everything, but it still has been an important step towards getting to that theory of everything. Okay, and so that's it for my exposition, and I will pass it on.
Should we maybe go, or Christian wanted to present a little, show some slides?
Yeah, maybe while Anushka, while you get ready with sort of the question, maybe I can just quickly share my screen, Jacob, if you can give me, I think the host keeps passing around. So I just wanted to show very quickly two web pages, and I'll put them in the chat too in a second. Let me put myself here. Sorry. Okay, I'll put the thing over here so I can see it. Share screen. Here it is. So there's sort of two things I wanted to highlight. The first one is that the physics division, so this is where we all work. We have actually every summer we host something called the QuarkNet workshop, and this is something that I think involves students and teachers, both, where you sort of interact with people mostly in the physics division, and you sort of see two of our sort of well-known colleagues, George Smoot and Saul Perlmutter. Both of them got the Nobel Prize. Saul is the person who did the experiment that discovered that the universe is accelerating, for example. Anyway, so this is one thing. The applications aren't out yet, but they should come up soon. So this is one thing that exists. And then here's another web page of sort of just high school programs that exist at the lab. This is now not just physics division, but the whole lab. And here's sort of a list of the various things that we have. Director's Apprenticeship Program. Here's a program that is specifically aimed at girls. Here is something where you can actually get some experience doing some research. And so on. So I'll just put this up here. I just quickly looked, and I think essentially one thing here has application deadline like today, but all the other ones at least are still, some of them, if you want to do this, you have to act fast because that's in 2 days from now. But all of those are in principle, I believe, still open to you. And so let me just put these two links. I'll put these afterwards in the chat. And I just wanted to show, this is the paper I think that Nick pointed out. Nick, is that right? So I'll post this. So if you wanted to get this, you'd have to pay $40 for it, but we have access to it. So I think I'll just download it and send it to you. But I think I have to go on the VPN of the lab, and I think it will probably kick me off the Zoom if I do that. So I'll do it after, and I'll send it to Anushka and Alessandra, and then you guys can maybe just send it out to everybody else if that's okay.
I already have a copy, Christian. I'll send that now.
Oh, perfect. Then you can just send it maybe right now, and then I don't know. Can you put in chat in the? I don't know if you can probably put files in the chat.
If not, I'll email. Yeah.
Yeah. Okay. Perfect. All right. So that's really all I had. If you have any questions, so some of those you have to read a little bit carefully. Some of those, for example, I believe this one here actually requires you to be nominated by a teacher. Some of these other ones you apply, some of them require a recommendation letter from a teacher. So you'll have to read a little bit the fine print on all of those, but I'll put it in the chat. So these are all possibilities here. If you want to do, maybe get a little bit more involved with some type of research. So, okay, I'll stop the sharing now, and I guess I'll hand it back to Anushka. Shall I make you the host, or
Sure.
who's going to host? You or Alessandra?
You sure make me the host.
You. Okay,
Alessandra's
perfect.
reception's a little wonky.
Okay, perfect. So you are the host now,
Perfect.
and I will just put the things in the chat while you put things up.
Perfect. Well, thank you for the opportunities. So what we have now are a bunch of categories which cover dark matter and the holographic principle and the theory of everything, etc. I was thinking that we could start with dark matter because Nicholas did go first. So the first question is just, what are some different candidates for dark matter? Like, what are axions, WIMPs, etc.?
Sure. So this goes back to this ruler I had earlier on. So I think that the idea, I mean, and obviously there's a lot to be said here, but just to really give you a brief version, the idea that's really dominated the field for a long time is that it could be a particle that's somewhat related to the particles we know about. And in particular, we thought it was a particle that was maybe 100 to 1,000 times the mass of a proton. And there was very good arguments to do with this as related to supersymmetry that Jacob talked about. But then we spent a lot of money and we've looked for it again and again, and nothing has shown up. So maybe it's still there, and maybe it just interacts a bit more weakly with the stuff we know about than we thought, and that search will continue. But I think really in the last decade, there's been an explosion of ideas where people think, well, okay, if it isn't one of these particles that's pretty similar to the particles we know about, just a little bit heavier, what else could it be? And so the next probably most well-motivated particle is the axion. And this is a very, very, very light particle. It has mass, as dark matter has to, but it is like, so the electron has a mass of like 500 and it's like an MeV, like 1,000,000 electron volts. So that is a half of that, more accurately. But then the best mass range for the axion is like 10 to the minus 6 eV, or maybe 10 to the minus 9. So it's like, 10 to the 12 or 10 to the 15 times lighter than the electron, which is like the lightest particle we know about. So it's unbelievably light. Like it'd be much lighter than the neutrinos, where we think they have mass. And so because of this, we go and do measurements, and we know how much mass is out there of dark matter, because that's what impacts gravity. So if I say that the particles that make up the dark matter are very light, I have to have way more of them to explain how much mass is there. And so this is why axions end up behaving like a wave, because there's just so many particles around, this collective description is more accurate. And there's various ways of seeing this, but it's sort of like in the electromagnetic spectrum, on the very low energy end, radio waves, you think about as a wave. But then on the very high energy end, gamma rays, you would think about those as photons, as discrete particles. And there's similar energetic arguments as to why that's the case. So the axions are probably the most well-motivated idea at the moment, but there's tons more. Like actually dark matter could just be a collection of black holes that are flying all over the place. And there's various ways of testing that. Part of that has been ruled out. And in fact, there's even the idea that you may have heard about that LIGO has observed colliding black holes. There's the claim that that may even be the black holes that are made to make up dark matter. And I mean, I think there's reasons why that's a challenging explanation, but it's not excluded yet. So that could be the case. Or even it could be that dark matter, I mean, an idea I've been working on recently that I think is interesting, it could be this extremely heavy particle that's so heavy it's almost about to fall into its own event horizon and become a black hole, but it's not there yet. And if that was the case, I mean, why this would be interesting is you just get startling signatures like these explosions happening throughout the universe you could look for. But this is, I mean, I've just mentioned a couple. In the literature, people have written down thousands of different types of particles that are dark matter. We've ruled out many of them, but there's many left that are yet to be tested. And especially for ideas like the axion, I think in the next 10 years are when we're really going to test some of the most interesting parameter space for the axion. So if that is what dark matter is, it's maybe in the next decade we'll really know for sure. So let me, it's a very interesting question, but yeah, let me leave it there.
Okay. Cool. And given that dark matter does have mass and it does interact with gravity, is dark matter potentially a medium for sound?
Good. So for a sound, I mean, my normal, like the normal way I have of thinking about sound is it's like a collective excitation in some sort of solid, essentially, or liquid you can have as well. What you can, so maybe if we go back to this sort of very light scenario, but normally if you think about a particle that's the conventional types of dark matter, so say around this GeV scale, which is where the proton is, we can calculate how much dark matter there is around. And it turns out that there's about 1 proton mass worth per centimeter cubed. So, I mean, this is, remember that sort of everyday objects, which is where sound waves form, have like Avogadro's number per gram. So we're about 10 to the 20 orders of magnitude short of really having large densities where, you know, they sort of go and bump into each other, which is how a sound wave propagates. So for most of the parameter space where we think about dark matter, you wouldn't be able to do this, but it's still an interesting suggestion. Yeah.
Interesting. Okay, so if dark matter were to be an
I think you muted yourself.
if dark matter were to be an element, what would it look like on the periodic table of elements, or even perhaps on the standard model?
Oh, good. That's a really interesting question. Yeah. So, yeah, when particle physicists, I mean, anyway, I won't go too far down this thing, but particle physicists think about things at the very fundamental level, right? But then there is all these, like we think about quarks and we think about electrons, etc. But then there are all these emergent states, for instance. So, for example, the periodic table is really all the different ways we can organize protons, neutrons, and electrons, where protons and neutrons we know to be made of quarks. So they're sort of these collective phenomena. A lot of what we think about for dark or emergent phenomena, what we think about for dark matter, though, is it's actually like a new fundamental particle, like a new quark or a new electron. And that's most of the thinking we have. But actually, sort of to give an analogy with the periodic table, it is possible that actually dark matter is made up of a whole bunch of additional particles. And actually, the state that we see that makes up dark matter is some bound state of these things, much like we have elements on the periodic table. In fact, there is some, I mean, pretty out there suggestion called mirror matter, where you have a complete copy of the standard model on the other side with slightly different particles. And then you can even have like dark matter can have like mirror oxygen and mirror all these other things. So this is, many instances of that run into trouble experimentally, but I don't think it's been completely excluded. So that's sort of one idea. And then the other idea about how exactly this fits into particle physics, like in this, the different ways we have of depicting the standard model, that's very much an open question. I mean, in the case of supersymmetry, it all works elegantly. Every particle we know about has like, all the fermions have a bosonic partner, etc. And the bosons have a fermionic partner, and dark matter would just be one of these. So this was a very nice picture, but it appears to be wrong. So instead, I mean, at the moment, we're thinking this axion particle, there's ways of fitting it in, but it's really the way it fits in is at much higher energies. In the world we live of, the axion is very different to the very other particles we have about, which is sort of indicated by how much lighter it is. So there's not as cleaner way of including it into the sort of way we normally discuss the standard model, but there are technical ways that they're related. So that's some thoughts on that point. Interesting question.
I think one thing you just see on all of this is that, while we know a lot about dark matter, we mostly know what it isn't, not what it is, right? So it's quite likely that the actual true nature of dark matter is none of the things that we've thought about so far.
That's a great
So maybe
point.
one of you guys will figure out what the right theory of dark matter is.
Yeah, and it's important to keep an open mind about like maybe we're just wrong about things, because we've had great ideas so far and they just haven't shown up. So it's a really good point.
So kind of adding on to the idea of dark matter and the standard model, there's this idea of supersymmetry. Could you talk more about what supersymmetry is? and yeah, and how we could maybe prove it.
Sure, yeah. So the basic idea, and I know Jacob is definitely an expert on this as well, so I'd be very happy for him to chime in and add on anything I might miss. But the basic idea is that we want things in nature to be as symmetric as possible. It just feels satisfying to have as much symmetry as we can in here. And it turns out that mathematically, like all the particles we know about in the universe essentially occur in two flavors. There's either bosons or there's fermions. And fermions famously obey the Pauli exclusion principle. For example, protons and electrons are fermions. And so this is why you get like the energy levels in an atom. They're really profound consequences of these basic properties. But so it's sort of, you might ask, well, why do we have these two types of particles? Well, actually, there's a symmetry that, I mean, maybe could have been better named, but we're stuck with, called supersymmetry, where you can actually map fermions to bosons. So they're now sort of related. So there's sort of now one object where you have like this super object where you have these two things related. And then the prediction is that for every fermion, there must be an associated bosonic partner. So there'd be a boson version of the electron, which is, because it's a scalar, which is a type of electron, it's called the selectron. And then there's like a boson version of the top quark, and it's called the stop. And there are other silly names for all the other particles. But then the very clear prediction here is that there's all these other particles. And then so we can go and look for them. And because it's a symmetry, you would expect that the scalar partner of the electron has the same mass as the electron. And we can go and try and measure, is there a scalar a particle that we can produce at a collider or something? And there's definitely not. And so it means then that if this symmetry is there, it has to be broken such that these particles are heavier. And there were good arguments that if the breaking scale would be accessible at the LHC or one of its prior predecessors. And it's a very interesting idea, but it just didn't show up in nature so far. So it could just be that actually it's much heavier, and generically it's needed for string theory is my understanding, so that we would think that at some level supersymmetry is there. Like if you got to high enough energies, you start to see the scalar partner of the electron, but we just haven't seen it yet. And now it's getting so heavy that there are reasons why it's probably not associated with dark matter, for example.
But one thing that's interesting about supersymmetry, how it relates to dark matter, that if there is there's sort of one extra symmetry that is typically added on supersymmetry, it's called R parity. It doesn't really matter. That essentially the amount of supersymmetry is preserved. That essentially means the lightest supersymmetric particle that is not part of our standard model is something that cannot decay into standard model because it has to decay to another supersymmetric partner, but there is no lighter partner. It can only decay to lighter particles. And so that would mean sort of a prediction of supersymmetry together with this symmetry called R parity, is that there should be a partner that is not part of the standard model that is stable. And that could then be dark matter. And because sort of for various reasons, you believe sort of that supersymmetry might be related to sort of the Higgs mechanism, and sort of it lives at the scales where we have so far looked. There was sort of a good indication that maybe a dark and sort of fit everything. A particle that had sort of those interactions with those mass would explain exactly the amount of dark matter that we see. Well, roughly the amount of dark matter that we see. And so this is why, and this is what we call a WIMP, a weakly interacting massive particle. And so, this was what people for a very long time believed. It's just, it kind of had lots of things that sort of seemed right. But, the nice thing about physics is, in the end of the day, it is not our heads that decide, but it's nature that actually decides what's true. And at least so far, it seems like that is not what nature is like, at least not in the most simplistic thing, because we've looked for that particle, and we just, in the Large Hadron Collider, we looked for so many supersymmetric particles, and we just haven't found any of them. So,
that's a really good point. Yeah, and just one other thing, I mean, in sort of Jacob's direction about supersymmetries. Okay, so we haven't seen it, so you might think it's just a dead area, but actually it's not going anywhere because it's an exceptionally useful calculational technique. Like, if you think about if you're trying to figure out how a ball rolls down the hill, you can imagine that that's a much easier question to answer than if you had some random jagged object and you're trying to understand how it would move. Like the presence of symmetry in problems makes things easier to solve generically. And supersymmetry is the same. It's a bit more technical, but it actually makes calculations a lot easier when it's present. So for a lot of the things Jacob was showing, I mean, sure, some of those objects he had were horrible and they're very hard to solve, but they're even harder without supersymmetry. So as a calculational tool, it'll exist for a long time yet. It's not dead on that front.
Okay, we have a question in chat, which is how do we verify the precision and accuracy of the Large Hadron Collider?
Christian's the expert on
Yeah, so maybe I take it. Ryan, can you just clarify what you mean, verify the precision? So how do we know how precise it is, or how do we increase the precision?
Yeah. Yeah, how do we know how precise it is?
Yeah, so there's really sort of typically two precisions that you talk about. So, we can do a measurement. So, for example, a typical measurement of the Large Hadron Collider is we look if we, so let's say we collide lots of things and we try to count how many times do we see a particle of a particular mass that interacts in a certain way with my detector? Okay, and now we just count, and maybe we now look for a particle that is not part of the standard model. So we look at a particle that has a different mass than anything. So we look for something that is not part of the standard model, and we can count, and then so far essentially the answer has always been, when we look for something that is not part of the standard model, we found zero particles. And whenever we try to look for particles that are part of the standard model, we can make a theoretical calculation, say how many events should we see that have this particle. And then if we do the measurement, we actually find that number of particles. So that's how we do things. Now, in all of those things, there's a lot of uncertainties, accuracies, and precisions involved, right? The first thing is I have to make a prediction, particularly if you look for particles. Let's do this. The second part, what I described, let's say we try to verify the standard model. So there's two things I need to do. I need to count the number of particles that I see, but then I need to check, does it agree with the prediction of the standard model? So I need to actually calculate how many events do I expect to see. And that is a calculation that has uncertainties. So you need to quantify how large those uncertainties are. And that's sort of some of the work that I do to make better calculations, make better approximations, or typically you do perturbative expansion, you go to higher orders in that perturbation theory. And so to make better calculations, we try to estimate what the uncertainty is. Then on the experimental side, there's lots of uncertainties too. These typically go into two categories. They're called systematic uncertainties and statistical. So let me just unpack that quickly. What a systematic uncertainty is essentially, how well do we understand our detector? There might just be some things in our detector that we don't know exactly. And so these are typically systematic uncertainties. That's one thing. And so experimentalists do a lot of work in trying to understand their detector better. And then the second thing is what is called a statistical uncertainty. It's the thing, if you try to flip a coin, you should find, if you do 10 coin flips, you should find 5 times heads, find 5 times tails. But of course, if you do the experiment, you almost never find 5. Most of the time you find 6 and 4, or sometimes 7 and 3, right? And that is a statistical uncertainty. So the more experiments you make, the closer you will get with that coin flip to half-half. And that is a similar thing. And there, the only answer is run longer, do more measurements to do that. So there's an enormous amount of work that goes into, I would say, probably certainly of experimentalists, I would say probably 95% of their effort is actually going into quantifying that uncertainty that they have. And so, for example, when we as theorists, as in the field actually claim that we've discovered a particle, there's sort of a very clear definition of what that means. It's called 5 standard deviations. So that essentially means it's essentially certain probability that you ask the question, if this were just pure statistical fluctuation, if you can do this calculation, if you throw a coin, how likely is it that you'll get 10 times heads and 0 times tail? You can calculate what that probability is. And essentially what we are saying, how many times do we, what is the probability that what we saw could just come from such a statistical fluctuation. And so that's one thing. And then the second thing is the systematic uncertainty. And the third thing is the theoretical uncertainty. So there's an enormous amount of work that goes into that. Good. Does that answer the question, Ryan?
Yeah, it does. Thank you.
Perfect. Thanks. Anushka had another question.
Christian, before you move on, can I add one thing to that? Yeah, I think just like a big picture thing. We actually built 2 detectors at the LHC just in case everything got mucked up, right? So you want to make sure maybe they missed some systematic on one side. They actually built 2 very different, like they were designed independently, instruments at the LHC, and both of them saw the Higgs. So this was like, even if you're worried one group completely mucked things up, it gave us a huge amount of confidence. So.
Yeah, that's a good point. It's another thing we do in science is, you want to be able to reproduce it. So, if some experiment sees something, many times, in this case, you cannot build many LHCs. It's very expensive to build an LHC. And so they made a point of just putting 2 detectors that are essentially identical, but many smaller experiments, maybe you just build one experiment, people find something, and then there's other experiments to then try to go and verify this. For example, there's famously an experiment where, experiments have claimed to have found dark matter, and then other experiments go and try to verify it, and then they don't see it, and then maybe the 2 experiments compare, and then you realize maybe the systematic that another experiment is missed or something. There's Nushka's question, why isn't there symmetry when it comes to bosons? Yeah, I don't know what is the right way. Nick, do you have a good answer? I'm trying to think what is the best way to explain it. So
the first thing I would say, I'll go ahead, Christian. Yeah, go ahead.
Yeah, so I think there is a so there is a very particular, so the standard model has a very particular structure, and there's many things here that are not that we can't explain from symmetry. In particular the number of bosons. Why? So we call this gauge theory, or the theory of the standard model, it's called, anyways, there's 3 gauge groups, and there's U1, SU2, and SU3. Why these numbers? Why it is these 3 gauge groups? I don't think anybody has any idea, but it's just right. Every measurement that we've done is true. If you remember from my talk, we've shown that I've shown you there's sort of 3 generations of 3 generations of quarks, 3 generations of leptons. I don't think anybody knows why that number is 3. There's many questions that we don't understand. There's a particular pattern of quark masses. While we do know they come from the Higgs, so in other words, different particles coupled with very different strength to the Higgs particle. We have no idea why there's such a wide variety in this. So there's still many unknowns, and many people try to explain those with a symmetry. And sometimes we can do those things, and sometimes we cannot. For example, the beautiful thing one of the beautiful things of the standard model is that there's a lot of particle, hadrons that we see. And back in the 30s, there was a zoo of particles, and they kept discovering more and more and more particles with all sorts of random properties. And then at some point, once you understood the strong interaction, there is a really beautiful symmetry in this gauge group SU3, and then you can start to actually, and various other symmetries, and all of a sudden you saw these patterns emerge. And so people really do believe that there's probably a lot more symmetry to be discovered. For example, these three different, the electromagnetic, weak, and strong force, they're not directly related to one another. So people think there might be a sort of a grand unification that happens where all these 3 gauge groups sort of come from the same symmetry group. But so far we haven't found any evidence of that. You can then make a prediction. If this were true, then you would have, for example, you'd have to find that protons are not actual stable objects. And people have looked for a very long time to see a proton decay into something, and they've never seen it. And so anyways, so this is a very good question, but that we just don't know the answer to. So Nick, did you want to add something?
I think that's pretty comprehensive. Yeah.
Okay. One more question about supersymmetry. So if we do prove supersymmetry, what are its impacts? What does it mean for the future of physics?
There's different ways of interpreting that. I mean, one thing is it means there's many additional particles, for example, but also I would probably think it's a hint as to like what exactly might be the quantum theory of gravity. I think Jacob could probably say more about this, but it is generically seems to be that a lot of these best predictions we have predict supersymmetry. So if we end up seeing it, I mean, besides the fact that we've discovered, you know, immediately every particle we know about has another copy. So we've like doubled the number of particles we know about. So that's a reasonable achievement. It also is hinting towards what might be happening at much higher energies where strings might live, for example, that we're not sure about yet. I mean, one thing that would be very interesting about this is if you know there's many additional particles, then in principle, even though, you know, they can't have a huge impact, or we would have seen them already, there might be all sorts of additional subtle phenomena that they're impacting. So it'd be very interesting to think about it from that perspective. But yeah, maybe it would also be an achievement just in its own right, discovering twice as many particles as we already know about.
It's also maybe Jacob could talk about, so supersymmetry is actually pretty special symmetry. So there's something, you know, this would sort of be the first sort of, maybe you want to say a little bit of what's special about supersymmetry.
Right, sure. Yeah, so let's see. So I would say that there's really, yeah, okay, so I'll start with this, is that we have the gauge symmetry that Christian was talking about. So that corresponds to the forces. So there's color, weak, and electromagnetism. And then you can ask sort of a question of, well, what other symmetries are there in nature at the fundamental level? So there are the gauge symmetries, which correspond to the forces. And then probably you've heard about the idea that there's also Lorentz symmetry, which comes from special relativity. So that seems to be, as far as we can tell, another fundamental symmetry that, you know, even the string theories that I described, they all start from this perspective that you have Lorentz symmetry. So there's actually one professor at Berkeley that kind of pushes this idea a little bit and says, okay, maybe you shouldn't have special relativity as one of your fundamental ideas, but that's a side topic that's also very interesting. But anyway, you can ask other questions like, what if I have Lorentz symmetry as my symmetry of spacetime, what other things can I include in there that kind of are as fundamental as Lorentz symmetry? And really, it turns out that the only way to really extend Lorentz symmetry, this idea of special relativity, is through supersymmetry. So it's kind of the unique way to actually extend the Lorentz symmetry of our universe, or of the standard model, however you want to look at it. But then there are a number of other kind of special things. So this kind of ties to what Nick was saying, that when you have supersymmetry, your models get simpler and you can do a lot more amazing things with it. So with regards to that, we could also say that supersymmetry might be related to the vacuum energy of the universe, or what we would call dark energy. So if we have regular supersymmetry, if supersymmetry were exact, then the quantum theory that you have would predict that we have no vacuum energy whatsoever. In order for supersymmetry to be exact, you can't have a vacuum energy. Now, this changes a little bit when you bring in supergravity. So if you assume that you have supersymmetry and gravity, which of course, if supersymmetry existed in our universe, we would have supergravity, in which case you don't have to have it as exactly zero, but then there's still a very interesting question of, well, how do you actually generate a value of dark energy that corresponds to what we see in the universe? And so what people typically do when they're trying to derive some kind of particle theory from string theory is to figure out exactly how to do this in a consistent manner and break supersymmetry, because it seems that in many scenarios, supersymmetry and the vacuum energy that you get are intimately related, and you often worry when you're trying to build a theory that you'll create a cosmological constant or value of dark energy that's too large. So those are just some aspects. The other aspects that I'm thinking of for why supersymmetry is special really relate to a lot of calculational tools that that Nick was describing. So just to say one thing in kind of that direction, in the canonical example of holography of ADS-CFT, the boundary theory that I was describing that lives on the label of the soup can, that is actually a supersymmetric theory that has what's called n equals 4 supersymmetry. So for particle physics purposes, we model things as what's called n=1 supersymmetry. So what this corresponds to is what Nick was saying, is that you have a boson and then you have a fermionic partner. However, you can extend this idea to have more supersymmetry. So this is kind of the idea of adding more and more symmetry as much as possible. But for particle physics purposes, there gets to a point when you're adding too much and things don't work out anymore. But in the case that I'm describing for ADS-CFT, is that when you have this n=4 supersymmetry, that is actually related to the very intimately with the notion about why there is a holographic dual for that. So the supersymmetry is also intimately related with this idea of holography. But there's a lot of intricacies here that I'm not delving too much into, but those are some reasons why supersymmetry is very special.
So Nick, you probably want to grab the last question from Ryan there.
Yeah, sure. 2 seconds. I just added this reference to the paper that I was mentioning earlier by Freeman Dyson. I was looking at, there's a few more equations than I recall. So I wouldn't expect you to follow every detail, but it's a pretty nice example of like theoretical work. Like you can sit and just calculate, could an experiment even exist to do this? And you can answer no, which is pretty satisfying and saves a lot of taxpayer money in some senses. So there's a question from Ryan saying, if there is matter and antimatter and dark matter, could there be anti-dark matter? The answer is absolutely yes. And actually dark matter could be its own antiparticle. So there are certain particles that can obey that. And what's really useful about that is that, so what happens when matter meets antimatter, it explodes and you get energy coming out. So what if dark matter could do that? Well, that's one way we could actually detect it, is that if occasionally, like as I said before, it's very sparse in many, in many of these models. So you don't have, it's so dense that it's just exploding all the time. But occasionally one of these particles would meet each other, they'd explode, give you some energy. And so actually, I'd say the majority of my research is looking for this. Like you can use telescopes at different energy ranges to try and see if there's any signal of dark matter crashing into itself and releasing energy. Because we don't know exactly what energy range that would look in, we have to search broadly. And while it's probably not the discovery of dark matter, a lot of my time is related to, if you look in gamma rays, which is in GeV, so photons that are about 1 billion times more energetic than the optical photons we see, you find that there is way more of those coming from the center of the Milky Way, where we think there should be a ton of dark matter than we predict. So there's actually the possibility that this is not only is it possible, it's happening and we've already seen it. But of course, then you need to get back into these details. Christian was saying, like, do you really trust all your background predictions? How trustworthy is everything? It's a very messy business, but it's a really nice insight there. It absolutely could happen and maybe already is. Yeah.
The question from Anushka. So in principle, yes, there could be, well, so neutrino could in principle be dark matter, but it's just way too light to be the dark matter part, to make up. I mean, so to some degree, if you want, a neutrino is part of dark matter, if you want. It's just a teeny tiny fraction of what we actually need. Yes. But yes, this is the kind of thing we're looking for. We're kind of looking for something that looks kind of like a heavy neutrino, if you want.
Yeah, it's actually a really nice argument you can make. Like, I say the neutrinos are light. How come they can't be dark matter, but axions, which I said are much lighter, can be dark matter? This actually goes back to this fermion boson distinction that I said earlier. And so fermions obey the Pauli exclusion principle. So you just can't pack infinitely many of them into any space. So they all have to have their own state that they exist in. So you can actually calculate how many fermions could I pack into a galaxy. And then you can calculate the number for a given volume. And then to get the mass of the galaxy, I multiply it by the mass of the dark matter particles. And if you do that for a neutrino, we know roughly what their masses have to be. You fall way short. So you can actually, I mean, it's again, sort of like a thought experiment. You can determine that neutrinos couldn't be dark matter, although otherwise they have all the right properties. They don't interact with light. They're very hard to see. Yeah, so as Christian said, a heavier neutrino absolutely could be dark matter. It's one of the ideas that people talk about, something called a sterile neutrino.
Very interesting. Okay, those are all the questions we have about dark matter and supersymmetry. We have a couple more. These would be more directed at Jacob. So next question we have is, what are some general theories that we have to try and unify the general theory of relativity and mechanics, other than string theory, perhaps even?
So
Quantum
sorry,
mechanics, I mean, I assume, right?
yeah, quantum mechanics, right?
Mhm.
Yes. Okay, good. So let me make sure I understand the question was, what alternatives do we have other than string theory?
Yes, and how are we trying to unify?
Yeah, well, okay, so well, on the unification front, I would say that that's probably the more interesting question. So you know, you can try and develop models for unifying the forces without necessarily including gravity at first. So these would be the so-called GUTS, so grand unified theories. So you would have some kind of what we call gauge interaction that somehow encapsulates all the other forces that we see. So of course that would be color, a weak force, and electromagnetism. So there's been a lot of work in developing that. So what that comes down to is is basically, to put it in kind of a jokey manner, is how to fit smaller matrices into bigger matrices, I guess is one way to describe that. So there's been a lot of work in figuring out how to do that in a consistent manner and have some kind of good predictions for those. So that is very much a particle physics way to develop it. But then if you want to try and say, okay, I have a grand unified theory, I know how the three forces we see, how they unify into some other larger or more, more unified force, I should say, how do I combine that with gravity? I would say that there really isn't there isn't really another alternative other to string theory. So you might have heard of something called like loop quantum gravity or something like that. So I do not know much about loop quantum gravity other than what I read on Wikipedia, like maybe when I was in high school or something like that. So it's been a long time before I even looked at that concept. But from the last thing that I know about loop quantum gravity is that there are two problems. So one of them is that this may be outdated. Maybe there's been recent progress, but not many people work on it. So usually I don't hear too much about it. But the last I heard is that loop quantum gravity cannot correctly reproduce Einstein gravity. So when you have when you propose some kind of more fundamental theory, you should be able to show that in some kind of limit, you get what people knew about, right? Because we see, you know, it's the same sort of idea that originally we thought that, you know, regular Newtonian gravity was the theory of gravity, but then you know, well, Einstein developed the ideas and then showed that there are observational consequences of it. But once you confirm that there is some better theory, that better theory had better reproduce what everyone else saw before that better theory came along. And so that what I understand from loop quantum gravity is that there isn't a way to show that loop quantum gravity gives rise to what the gravity that we know about, which is Einstein gravity. So that's a big problem, because if your proposed fundamental theory can't produce what you see or what we know about right now, then you question whether it can be valid at all. So that's one issue. The other issue is not necessarily a critical statement against something like loop quantum gravity, but the thing is that string theory doesn't just provide you a theory of quantum gravity, but also provides you a framework for understanding everything in terms of the particle content and the various forces, whereas loop quantum gravity would be only about quantum gravity. So if you have to decide, well, you know, based off these two facts, if you had to decide which one you would think is the more likely scenario, I would think that, you know, string theory is the more likely kind of fundamental theory, because you have a way to understand not just gravity, but other interactions as well. And you can actually reproduce Einstein gravity, which is, again, kind of the essential feature. Oh, so I will make one other comment, I guess, is that there are weird theories of gravity, but they are not Einstein gravity. And as far as we know, they don't have any direct significance for our universe. So they wouldn't be things like what you were asking, which is like an alternative fundamental theory. They're just other weird mathematical constructs that might have some significance to other things that we know about through some kind of dualities, but they're not gravity in the way that we think about them.
Got it. So, well, kind of on this idea of the theory of everything, it's about trying to unify quantum mechanics and general relativity. But why do we need to do this if Einstein's theory already explains the world?
Okay, so what I would say is that Einstein's theory, so Einstein's theory here, talking about the general theory of relativity, is that it is a classical theory that does not involve quantum mechanics. So it describes lots of phenomenon, but it is not a quantum theory. So then what you want to do, since we know that quantum mechanics is a fundamental aspect of our universe, is that we would want to combine what we know about general relativity with quantum mechanics. So that's why we want a quantum theory of gravity. Now, you can kind of interpret this question also in the sense of why do we even care about a quantum theory of gravity, or why should something like that even exist? And the reason for that is kind of goes back, well, I would say kind of an analogy to that goes back to the Fermi theory for the weak interaction. So for the Fermi theory, it was kind of a effective way to look at the decay of particles. So for instance, thinking about like beta decay, for example, is that you had a way to kind of do effective calculations, but people knew that it couldn't be a fundamental theory because it was not, they would say not renormalizable, but you can kind of think of it as the notion of that it would be valid for some energy range, but wouldn't be valid for all possible energies. So we knew something weird was going on with the Fermi interaction, and what that kind of understanding developed to was the weak force, actually, was that there was something that we needed to kind of include in the Fermi theory to complete our understanding of beta decay and other phenomena. And so I would think that you can kind of put that in a similar footing with the question about why should we care about quantum mechanics and gravity, and that you can kind of come up with an effective description of the interaction between gravity and quantum mechanics. So this is not a very hard thing to do. Actually, you can just you can do some very basic stuff and come up with something that looks like gravity and quantum mechanics are working together, and that'll work at low energies. But the problem then is if you say, okay, I want this to be true for all energies, so I want this to describe gravity and quantum mechanics together, no matter what the energy scale is, then the thing that you'll write down will not work unless it's string theory, because that seems to be the only thing that will actually work. So did that answer the question? Because I think I lost track of the original phrasing.
Yes.
Okay, good.
Okay, well, kind of, sorry. Going on, you started talking about decay, and there's actually a question, which is, in string theory, is it possible for particles to decay into dark matter or vice versa?
Yeah, sure. So, I mean, it's certainly possible, because what string theory is doing is that it's not superseding, it's not saying that our regular way of understanding particle physics is wrong in our kind of low energy way of understanding things. So for an interaction like dark matter decaying, or something decaying into dark matter, we have mathematical tools to figure out how to describe that. And what string theory does is that it says at high energies, you have to change how you do your calculations, but at low energies, you get essentially the same thing. So you can describe things like something decaying into dark matter or dark matter decaying into something else in string theory, and you'll get pretty much the same answer you would get in the standard way of doing stuff. Maybe some corrections, but usually those should be minimal at best.
Maybe I can just quickly, so I think this thing that Jacob said, so first, certainly if you think of supersymmetry, which is sort of what would happen at low energies in a string theory, certainly, if the way we would try to look for dark matter particle is typically we produce some particle. Remember, I told you it's sort of the lightest supersymmetric particle would be dark matter. And so really what we'd actually do, what would happen in a collider, we produce some other supersymmetric particle and would keep decaying into lighter supersymmetric particles until at the end it hits that lightest supersymmetric particle. And so certainly there is, particles decaying into that particle. So that's certainly a possibility if there's other particles around. Now, of course, if there's only a single extra particle, and that might be the heaviest particle, then nothing would decay into it. So I think another comment I just want to make on what Jacob said, he said sort of at low energies, things look like just the standard model. This is actually really important concept. I sometimes read that people say, why do we still learn about Newton's gravity if we know that it's really relativity that is true, right? And so why do you guys actually learn in high school about, Kepler's laws, right? That's all based on, has nothing to do with Einstein's theory of relativity. And we kind of know that the right theory of gravity is Einstein's theory. And the answer is essentially what we often call effective field theory. So that means if you look at something from a far distance, look at it at low energies, it just kind of looks like Newtonian gravity. So Einstein's gravity sort of reproduces all the same effects. It doesn't look any different from from Einstein's gravity at the distance scales that we look at things. So I think that's a really important concept to always keep in mind. And my favorite example of this is something that, of an effective theory. You probably have learned at some point that if you have sort of a charge that sits somewhere, sort of electric field lines go out from that charge, and there's sort of a conservation of how much field goes out. So now you can ask the question, but imagine that charge that I have down here is actually some atom that has a charge, right? There's really many protons in there, many electrons, so it's not really a point. So the calculation that you always do is a point charge that has absolutely no extent, and then sort of you have these radial field lines going out. But the whole idea is if you have some sort of charge distribution, some small ball that has lots of charge inside of it at various different points, well, if you look at this from far enough away, that ball just looks like a point, right? And so if you're really just trying to understand what does the electric field look like far away from that object, it is perfectly okay to treat that object as just a point. And so that's really this idea of an effective theory. So there's nothing wrong with saying radial electric fields are radially symmetric. That is true until you probe it with either enough precision, or you go close enough, right? So this is really something, and I think it's a really important concept. You don't need to do the most complicated calculation every time. You should always include the physics that is relevant to the problem you're just trying to describe, and not something much more complicated.
Okay, Ryan had a question about the Big Bang Theory. In the Big Bang Theory, they mentioned super asymmetry. Is this possible?
So Big Bang Theory being the TV show, or not the okay. So super asymmetry. Is that that's the
oh,
the
sorry,
term?
Brian, I totally misunderstood your question. So okay, I missed the A.
So the only thing I could think of that could be real about that would be you have some kind of theory of asymmetric dark matter that's supersymmetric. I mean, I don't know if Nick or Christian have a better interpretation of what that could mean.
It sounds like a paper that would appear on our, we have this archive where everybody posts papers. And it's actually quite interesting to try to look at that on April 1st, because you always find a couple of interesting papers. And that sounds to me like a paper that could appear on April 1st. Maybe Nick and we should think about writing a paper on supersymmetry.
There was an
we have what, 2 weeks to go, a week to go?
Yeah, get one out. There was an April 1st paper last year where somebody had a demonstration of room temperature superconductors. And what they did is they made a little room and they cooled it down to very cold temperatures and had a demonstrated superconductor in there. And they put this on the archive. So that's the sort of thing that comes out.
Yeah, so I guess the answer is nothing that I know would be called super asymmetry. But yeah, like Christian said, people like to come up, even if it's not April 1st, they like to come up with creative popping names. So I would imagine that maybe at some point someone's going to say something like that.
I mean, I think it's interesting on the show. There's actually, I think, several of our friends who are probably UCLA and at Los Angeles-based institutions, I think, are sort of advising the show and coming up with thoughts for the show. So.
Don't they invite physicists in to write the whiteboards occasionally? I mean, I know a physicist usually does that, but sometimes they get volunteers in, other physicists to write the whiteboards on. So they usually have access.
Yes.
Yeah.
I remember actually when I was a grad student, the whiteboards in Good Will Hunting, those were actually written by a professor at the institution I was in Toronto. Which was actually quite fun. So that whole movie was actually shot in the physics department in Toronto. So, I was there when that movie was shot and there was Matt Damon running around. Anyways, it was pretty fun.
Felipe has a question, which is, what are all of you currently working on?
Who wants to go first?
That's what I was thinking.
Okay, I can. So, a lot of my work actually at the moment is, as I mentioned, I think when I gave the talks, a lot of my research is sort of related to the question I answered earlier, how well do we actually know what we should see at the Large Hadron Collider? So if we make if they measure something, how can we compare to the standard model and then actually check whether it agrees? So that is essentially about developing new ways to do calculations, to make calculations more precise. But typically what I like to do is think about new ways of doing something rather than just doing a more complicated calculation. But then, as I might have mentioned the last time, so I've actually started to think quite a bit about quantum computing recently. And this is not something I can now get into. Maybe we can do this some other time. But essentially, sort of one of the big questions, I'm sure you've heard about quantum computing. And so one of the questions that is, what are sort of the interesting problems that you might be able to solve in physics if you had a quantum computer, or well, we have a quantum computers, but at the moment these quantum computers are probably not big enough or not powerful enough to do any, anything that a classical computer could not do. But what are the interesting problems that you could really do if you had a good quantum computer? And so there is an enormous amount of work of sort of developing theoretical research and so on. So that's actually where I spend quite a lot of my time on at the moment.
Do you want to go, Jacob?
All right, sure. So yes, let's see. So I guess what I should talk about is probably my most active projects at the moment. There's always kind of like a laundry list of stuff that you want to do, and that some take priority over the other one. So on the list of most active stuff right now is a good portion of my work has been related to axion dark matter. And so that's one of some of my most active projects right now are about ways to detect axion dark matter, or if you detect it, what kind of interesting things can you learn about, for instance, the evolution of the universe or other aspects of the universe, or even, for instance, how to motivate further experiments, assuming that we do detect axion dark matter. Because like Nick said, is that we're really getting into an era of a whole bunch of incoming data over the next few years or decade or so of information on the axion as potentially as dark matter, or even particles that are that look like the axion but might not be completely dark matter. So that's kind of one classification of some of my more active stuff. And then on the more stringy side, this is a little bit different than what I normally do. So normally I'm interested sort of in these questions of how can I get some viable information about particle physics from string theory or string construction. So, or not just particle physics, but also cosmology, which I think is kind of a much more interesting question right now. And especially if there's a lot of discussion of, can you even have things like dark energy or inflation in string theory? So these are very neat questions. And I have some things that I've been dabbling in on that front, but it's not probably my most active set of projects right now. Instead, one of my more active things is a little bit different, which is tied to these kind of weird theories of gravity that I described towards the end of my talk. So there's, again, this holographic principle where you can relate d-dimensional theories to d-1 dimensional theories. So, the soup can, and then the label of the soup can. And so that people have studied that a lot over the past couple of decades, but there's actually a completely new way to do this that was really just put forward over the past couple of years, which is, yes, how to say this. So so rather than go kind of the overall picture, I'll kind of be a little bit more specific. So the thing that I'm working on is that is this a case where you have a three-dimensional kind of soup can and then a two-dimensional sort of label. So it's very much the picture that I showed at the end of my PowerPoint. But what's happening is actually the soup can is not a soup can, but it's actually a donut. So you've got a kind of curled up thing instead. And what you're doing is that inside the donut, there actually isn't any kind of gravity whatsoever. So there's no kind of gravitons, nothing like that actually exists in there. But it's still some form of a quantum theory of gravity. The way that the gravity shows up is that you're actually do a sum over the different types of donuts. So you can think about a donut as changing kind of the radii or a little bit of the structure of the donut. And if you think of a quantum gravity theory as a sum over shapes instead of as like a graviton, you can actually get a notion for that three-dimensional theory. And then you have a very weird sort of two-dimensional dual theory, which is actually related to, somewhat related to stuff that I've done in the past with string theory and particle physics, that the two-dimensional theory is a conformal field theory. So that's a little bit what I mentioned in my talk. But it has numbers in them that are undetermined. So these are things like, in the string case, they would correspond to things like the radius of compactification or other parameters. And what it turns out that what you have to do is you have to average over those kind of numbers, and that gives you a new kind of dual theory to this weird donut shaped thing. So the description is very weird, but that's because it's a very weird sort of thing. But it's pretty neat because, like I said, this is something that's really only, this particular thing has only existed for less than a year, actually. And so there's kind of a lot of opportunity for new explorations in this direction. But yeah, that was a very sort of a rough overview of what it looks.
Awesome. Yeah, maybe I can go last. So most generally, the question that is driving my research is, what is dark matter? And the way that I like thinking about it is sort of in two fronts. One of these is looking for these signals in astrophysical data sets. So there was this nice question earlier about whether dark matter can be its own antiparticle. So one way we could look for it is through the signatures that could be generated by that. But then we don't know where to look. So I look in X-rays, I look in gamma rays, I even look in some of the most energetic particles that we've ever seen in the universe. So there is this proton that we measured, I think in the last decade, which had an energy that did exceed the kinetic energy of a baseball pitch. So it's an obscenely energetic particle, and we have no idea where it was generated or where it's from. It doesn't yet mean that it's dark matter. It could be something else, but this is the sort of direction I think about. And the other area is related to this axion dark matter, which I talked about earlier, where you really need to think about it differently because qualitatively it behaves very differently. It behaves like a wave. And so again, this is sort of what Jacob said. What's nice about this being a new field is that people just haven't thought about this as much. So there's sometimes you feel like there's ideas where you're like, why didn't anyone think about this before? And an example of that I was thinking about recently was that if dark matter is a wave, well, then something that we do with waves all the time is we use the fact that they have both an amplitude and a phase to combine them to use the phase information to get more information out of it. And so if dark matter is a wave, you should be able to combine this phase information. And this is a process we call interferometry. And this technique is used in science all the time. And so I actually had a paper showing that you could perform interferometry directly on the dark matter wave if it behaved like that, and you could learn about what you're seeing and other aspects, for example. So I'm very excited about that direction because it just feels like this really could be dark matter, and we just haven't thought about it as much as we have some of these ideas like supersymmetry. So there's sort of some interesting new ideas to explore there. But yeah, this is the sort of question I think each of us could talk a lot about. So let me just stop there.
Yeah, so maybe quickly, I just put an answer to Sarah's question in the chat. So as I write there, I must say I don't know enough about what the problems are to understand smell, but I could actually see that this is something that this is possible. Essentially, what quantum computers are really good at is describing some dynamics of molecules, which are really difficult to describe using classical computers just because they're quantum mechanical. And then there was a question from Ryan. I would argue, I think Jacob can tell more of this, but I would argue that string theory is precisely that. It's the development of a new branch of mathematics to unify quantum mechanics and relativity. I mean, that's probably one way to describe string theory.
Yeah, no, I think, yeah, sorry.
And good.
Yeah, so I'll just jump in then. Sorry, I thought you were going to continue, Christian. Yeah, so for that, for Ryan, yeah, so for Ryan's question, no, I think Christian's point is a very good one, and it's kind of related to one of the things on my slides that unfortunately I didn't get to go much into is that there's so much interesting mathematics that's related to string theory that it's helped develop a lot of fields and has even led to really new connections between existing mathematics. And so that's one of the most interesting aspects of string theory, that you didn't necessarily expect that it would do that. So it's like we tried to develop, you know, a theory of everything or a theory of quantum gravity, and we got that, but we also got all these weird connections between different branches of mathematics and all of these new fundamental ideas. So yeah, you could say that string theory is kind of like the new branch of math that is developed exactly for this purpose. The only other thing that I'll mention is that very often it turns out that some, you know, brilliant mathematician came up with something like 100 years ago, and at the time no one knew what it was good for, and it turns out that it's absolutely fundamental to what we need to understand. So that happens quite a bit, and actually it's happened exactly with this this project that I mentioned that I'm working on for the very weird theory of gravity, is that there's a very brilliant mathematician, not quite 100 years ago, so like 70 years ago right now, who figured out a lot of the mathematics for what we needed. And so you just take those results and then apply them to the thing you're trying to do. So yeah, mathematicians often have a kind of foresight for very important stuff that we find very useful.
I would say this is always something that always intrigued me, that, you know, if you think about it, we're trying to describe nature, right? How nature works. This could be arbitrarily complicated. The fact that, you know, mathematics is actually able to capture all of that, I still find that, because to some degree, you know, I mean, these two things were developed sort of together, and right, as you said, right, we developed mathematics to describe some things, but I still find it, every time I think about this fact, that the fact that our language is actually able to capture nature is, I still find it actually mind-blowing. You know, that we as humans can actually just develop a language that allows us to talk about. It's something I always find fascinating.
We have a couple more questions in chat, and then yeah. So Aparna asks, what does a particle look like?
Now it becomes a question, what do you mean by particle? Elementary particle, or a particle like the proton, which consists of other particles? So, I mean, I can ask the question, or I can say, so essentially an elementary particle, that is essentially, I mean, the way we view it is it's literally a point that has certain properties. It has charge, maybe mass, but there's no extent to that particle. That is probably just our lack of, I mean, it could be that it actually really is a point particle, or it could be that we just haven't looked at it closely enough, right? That it's smaller than anything than the best microscope that we have can actually resolve. Now, many other particles that we have seen, we've looked closely enough, and we've actually started to see that there really is a structure to it, like protons. Proton is sort of the particle that you all know about. That is that example. And if you remember, I showed you in my talk the last time that the proton sort of consists of 3 quarks and gluons that sort of bind things together. And you know, and one of the really interesting questions is the electron actually a fundamental particle, or is it not? You know, it could be that at some point we realize, if we look very closely at the electron, it really isn't a fundamental particle. It consists of other smaller particles again. And, you know, to some degree, if you think about it, every time we've looked deeper, I mean, there's really no reason to expect why, you know, I mean, the way you can think of, remember from my talk, I said sort of looking closer is the same as probing at higher energies. Right. And so we've sort of now increased sort of maybe over the last 100 years, we've sort of increased maybe the energies we can look at by a factor of, I don't know, 1,000, 10,000 or something. But going up to this Planck scale that Jacob was talking about, there is many, many, many orders of magnitudes to the left, you know, like 16, 15, 16 orders of magnitude. And, you know, the way I would look at it is there's, you know, why should we expect that we sort of looked over 1,000, looked over 1,000 or 3 orders of magnitude closer at something, we started to discover all of these things, and what should be fundamental about just right now where we are, why that's sort of the end of everything. Everything, you know, at the scale that we can now probe, everything is a point. Now, it could be that that's just how nature made it, but then there's really this question, and that's sort of one of these questions, that sort of underlies, you can make a lot more fundamental and mathematical, like what is so special about the scale that we have probed up to this point? Like why this, this 26 kilometer circumference collider? What is special about 26 kilometers? Why don't we need so much larger in order to see what's going on? And so the answer is we don't know. And we need better. The problem is to go, what is special about the energy scale that we've looked at, that we can sort of build things at a size of 26 kilometers. Things get a lot harder if we have to go factors of 1,000 bigger than that, because then we're talking about the size of the Earth at some point, right? And so I mean, there is something, we can sort of build things at that size. It's much harder. So I think we need a whole nother technology probably in order to do something different, or maybe do things as how Nick is doing a lot of his research, actually look out in the sky and see, can we see sort of things that come by, that we actually see these heavy particles decaying somewhere in outer space, and we sort of reach particles. So it's a great question, and I don't think anybody really knows the answer to that.
Okay. We have one more question. I know we've already had you an hour over time. Thank you so much. So our final question today will be from Ryan. Can we use quarks in a sort of quark microscopy in the same way that we use electrons?
There's a lot of ways of viewing this. I'm sure both Jacob and Christian could say a lot. I mean, there's some technical challenge that having quarks on their own is a very hard thing to do unless you're at exceptionally high energies, because they have the strong interaction. So they want to just pull things together so that you can't see a naked quark. But in another way of phrasing it, actually, this is sort of what we do at the LHC. In the sense that, like, actually what you're doing there is you're crashing quarks or gluons or other colored particles together. Like, actually we collide protons, and really a proton is a collection of quarks and gluons together, and then a ton of stuff flies out. And then by ramping up the energy of the particles we're crashing together, eventually new stuff can be produced. Like, for example, the Higgs, we did that. And in some senses, like, it seems a bit crude, like crashing things together and seeing what comes out, but it's a technique that seems to work very well for us. And we've discovered many particles that way. So in some senses, we really are using quarks to probe the smallest distance scales we've ever seen. It's not a direct analogy with, like, tunneling electron microscopy. And for the reason I said, actually technically doing that is difficult, but probing even smaller distances than we can with those techniques, quarks are heavily involved.
Yeah, I think the answer that Nick, I think I would say exactly what Nick said. So essentially that's what we're already doing. But you can ask, why don't we try to do this in more everyday life? And essentially the electron is the most easily accessible point-like particle that we have access to. Well, the other one is the photon, which we use quite a lot to see things, right? But but yeah, so that's, I think, sort of in everyday life, I think the electron is the most obvious particle to use. It's a stable particle. We can control it. It has a tiny size, so you can really do it. The problem, if we were to use a proton, it would just be the proton has a size itself, right? And we're actually trying to, so that would sort of distort things. But yeah, I think everything else that Nick said is exactly right. We're sort of doing it already.
Wonderful. That's all the questions we have for today. But thank you so much for staying an hour over time and answering all our questions. This was really incredible. Thank you. And thank you everyone for coming.
It was a lot of fun. Thank you for being so engaged.
Yeah, thanks so much. And this was really great. So I encourage you, if you're interested in some of these outreach activities, these internships, have a look at these websites that I put in. Hopefully I think it's probably in the recording. It's in there. If you can't, just grab them out